Good morning. This is Jeffrey Rufus here to explain secure messaging, for example, XOR encryption and decryption with the help of Turing machines. Why do we need this? Because in this ever growing world of messaging and chatting and sending images and files through various means, we need more and more encryption and decryption and cryptographic tools for secure transcription. So for this, we are using multiple tools in the real world, and for this example, we are I'm going to try to explain XOR encryption and transcription with the help of a Turing machine. So how does Turing machines work? Turing machine, as we know, has an infinite tape, a read-write head capable of moving left or right. And I'm going to explain XOR. I'm going to have a tape alphabet of bits 0 and 1, and we'll see how it works. And we have our problem statement of how can XOR based encryption and decryption be accurately modeled with a single Turing machine framework. So we are going to do that. We are going to look at a framework of how it happens, and I'll then go into how the encryption and decryption happens in real time. So this is the state set overview, and this is the general diagram of how it happens. So we'll start, then we'll give the input a message X, then we'll encrypt it using XOR, which I'll explain in a few minutes. And after the encryption happens, we'll packetize it and we'll start to transmit it. Once transmit happens, if there's a 90% success, that is if 10 packets are sent, and if more than 9 packets are received, then we consider it a success. Else we consider it as packet loss and we go to the error handler. Then we try to resend it. If there is an error in the message, we drop the packet and end the message. If the message is 90% success, we go to the receive side. Then we decrypt the message and then we display the message to the receiver who receives the message. So initialization, the tape begins with our input image and with a secure key that the sender and the receiver each has for secure transcription. Then we encrypt the encrypt the tape with our key or hash as we call it using XOR. Then this is made into a packet and transmitted. At the receiver side, it is decrypted with the same key or hash that the sender uses, and the message is display and halted. If the transmission is met with errors, as we saw, is as a more than 10% packet loss, then we go to the error handler stage and the packet is dropped. Why do we need this? Because as I'm going to explain, Turing machines can fully work on XOR, and it works seamlessly, so we can do our XOR encryption and decryption without any issues. And this is just an example, as XOR is a simple operation, as we know from the Church Turing thesis that any algorithm can be made or depicted using a Turing machine. So that makes Turing machine a very powerful tool. So as we can see, we can use more complex ciphers such as Caesar cipher, RSA, and AES on Turing machine frameworks, and we can simulate multiple packet streams, and this makes Turing machine a very powerful tool for the help of encryption and decryption in the field of cryptography. So let's look into how exactly this encryption and decryption happens. We're going to see XOR encryption and decryption using Turing machine. So let's take a sample our message. Let's say A is our message, and we are going to encrypt it using XOR. So A XOR B is our encrypted message. Encrypted message. Now what is this B we use? B is the key or hash B is the key or hash that both the sender and the receiver have, that is used for secure transmission. So we are going to implement this using Turing machines. So for example, let's take an input as 0 0 1 1 0 1 followed by a blank symbol, and this is our A, our message, and this is our key that is equal to the length of A, and we'll assume our key as 11011. The length of this is 5 and the length of this is also 5, and this is our key B. Our key or hash is this B. Then we'll have our output which gives our encrypted message. We'll have this as 01101 B followed by 11011 followed by a blank symbol and our encrypted message. For that we'll construct an XOR truth table. For that we'll have 0 0 and 0 0 1 and 0 1 1 1 0 1 1 1 0. So our output will be 0 and 1 will give us 1, 1 and 1 will give us 0, and 0 and 0 will give us 0, and 1 and 1 will also give us 0 and 1 will give us 1, 1 and 1 will give us 0, 1 and 0 will give us 1, 1 and 0 will give us 1, 0 and 1 will give us 1, and 1 and 1 will give us 0. Okay, let's check. This is of length 5 and length 5 followed by a blank symbol. So this is our message, our key or hash, and this is our encrypted message. So 0 and 1 gives us 1, 1 and 1 gives us 0, and 1 and 0 gives us 1, 0 and 1 gives us 1, and 1 and 1 gives us 0. So this is our message, this is our key or hash, and this is our encrypted message. So we are going to implement this using Turing machines. So let's start. So how we are going to implement this? So we have a starting state. We have a starting state and start. Now when this input tape reads 1, we are going to replace it with a replacement symbol of P, and we'll name this, we'll name the states later. We'll have a state, or we have another option. When it reads 0, we'll name it as P. When it reads 1, let's name it as Q. When it reads 0, we'll name the state as P. So when it reads 0, needs to go to the second string and read the first element. So let's loop through all the zeros and all the ones. Then we'll read the blank symbol between the message and the key. Then we'll go to the first message, the first element of the key. So when we read 0 here, we are going to replace this with R, and when we read 0 here, we are going to replace it with R, and when we read 1 here, we are going to replace it with S. Okay, so in this, while coming for the second loop, we will notice that when we take the second element here and the second element here, this element would have been replaced with an R or an S. So we would loop here with an R, replace it, keep it as the same R and go next. Same as S, replace it R, replace it with an R and go next. S, replace it with an S and go next. Okay, so we've seen that the first element we read is 0 and then we are reading 0 and 0 or 1. So we'll handle this later. So when we read 1, we'll do the same. When we read 1, we'll loop through all the zeros and the ones and we'll go to the second string, and that we loop through all the R and the S, and then we have two options: 0, we can read 0 in the second string, that will be replaced with an R, or we can read 1 and replace it with an S. As we can see with an XOR table, 0 and 0 gives us 0, 0 1 gives us 1, and 1 0 gives us 1, and 1 1 gives us 0. So what we are going to do, we are going to replace these 4 states into 2 states. So what we are going to do is 0 0 0 0 gives us 0, so, and 1 1 gives us 0. So we'll connect this as both the states will go to the same next state. Okay. As for this, we both connect this. Okay. Now we have read both the symbols. So what we are going to do, we are going to loop to the rest of the key. So we are going to do 0 or 0, go right, 1 or 1, go right. We'll do the same here too. 0 or 0, go right, 1 or 1, go right. Now we have reached the end of the key, so we are going to read a blank symbol. Same here, blank symbol. Now when we have read the blank symbol, then we are going to the next available blank. So we have read the blank symbol, so we are going to the next available blank. So if a blank is there, because this is a 0 and 0, we are going to replace this blank with a 0 and go in the reverse direction. And we are going to loop this for any already computed 0 or 1s, and we are going to do the same thing here, 0 or 0, 1 or 1, and here we read 0 and 1 or 1 and 0, which gives us XOR of 1. So we are going to replace the blank symbol here, replace the blank here with a 1 and go in the reverse direction. So we have read corresponding element from the message and input from the key, and we have written the corresponding output. So we have to go back to our next input from our message. So what we are going to do, we are going in reverse. So what we are going to do, we are going to loop this back. We are going this back. We'll put this to a state first. So this is going to go in reverse. So as we know, it is going to loop through zeros, ones, and the replaced R and S. It's going to go in the reverse direction and going to pass through the zeros and ones and R and S, and it will go till the place where we have replaced with a P. So it will stop in a place where it encounters P. So what we are going to do, we are going to repeat this process. As we have encountered P, it will go to the reverse direction, and it will stop when it encounters, and B also will go. It will read through B's also. So we will go in the reverse direction and stop in the element that needs to be zeros and ones direction. It will go here, it will go to the left, and it will currently point to the element that was currently considered for XOR. So it will initially be P. So for currently we are not changing the element, we are just keeping it as P, and we are moving on to the next, or we are going to keep it as Q and moving on to the next. As we can see, this solves the XOR, and our stopping state is met when each of this element is replaced with a P or Q, and we read a B symbol here. So when we read B, we stop our tape, and we'll name this as Z, our final state. So we can name these states. We name this B, C, D, E, F, G, H, I, J. We have named the states. So this is what happens. As you can see, after this whole process happens, the input message and our key would have been shifted to P's and R's. So after this, our output would have been P, Q, P, Q, Q, P, Q, and followed by B, followed by S, S, R, and S, S, B, followed by our encrypted message, which is 10110. So if we want, we can convert our message and our key back to zeros or ones, but as we are only concerned about our encrypted message, I don't really think this is necessary. But if we really need it, we can convert this P and Q's back to zeros and ones. As you know, P corresponds to 0 and Q corresponds to 1. As we know, S corresponds to 1 and R corresponds to 0. This is a simple loop. We can convert the P's and P, Q, R, S to zeros and ones. So this is the process of encryption. So we keep this. This is the process of encryption. And now I'll tell how the decryption works. So as we know, we have our message. We have encrypted using XOR, and the B we use is hash or our key. So now we are going to decrypt the message. Okay. So let's see. So we have our A XOR B. This is the encrypted message that is transcripted for the receiver to receive. So this is not a literal message, so this is a secure way of transmission. So on the other end, our receiver will also have this key or hash, that is our B, and we use this wonderful property of XOR which states that A XOR B when done XOR with the key or hash will return our original message A. So this is the property we use in encryption and decryption, which states A XOR B, XOR with the key or B gives us A. So that is what the receiver will do with the encrypted message. He'll do the same XOR operation with the hash to receive A. So let's check if our algorithm works with that. So we have our A XOR B, which is the encrypted message, which we have as 10110. So let's take 10110. Now we are going to XOR this with our hash key, which is 11011. Now this should give us our original message, which is A. So let's go through this algorithm that we created to see if we get the original message. So what will happen first? So what will happen first is 1 will be read. Okay. So let's do this stepwise. So our first element is 1. So we go through this loop. 1 Q. So what will happen? We'll replace this 1 with Q. Okay. Now we'll loop through all the zeros and ones and we'll keep it intact. We'll loop through all the zeros and ones and keep it intact. Okay. Then we'll replace this XOR with a B in the input tape. So we're going to this. Then we read the B. Then when we read the B, we are skipping that. Then we are going through all the R's and S's. As we know, there's no R's and S's because this is our first element. Then we are reading a 1. So we are reading a 1 and replacing it with an S. Okay, done. So what we are going to this loop. So what we are going to do, we are looping through all the zeros and ones. And after the B, we are replacing the B with 0. So we have our first element, that is 0. So which matches with our input, that is 0. Okay. This gives us 1 which is replaced with Q and 1 we replace it with S and we get an output of 0. So what do? We read this 0, we converted the 0, then going in the backward direction, we are looping through all the inputs and we are going back to the starting. So what we'll do, we'll read this 0. 0 will go to this and we are looping through all the zeros and ones. We'll read the blank. Then what we are reading S. We are looping through all the R and S. Then we are reading 1. 1 will take us to here, and which will give us, we are replacing the B with 1. So we have 0 and 1. As you can see, our second element of our input message is correct. So as we repeat this process, we go to repeat this again and again, and we get 1 for 1 and 1 we get 0, and 0 and 1 and 1 we get 1, and 1 and 0 we get 1, and 1 and 1 we get 0, and 0 and 1 we get 1. Let's see. Yeah. So which gives our final output here as 0 1 1 0 1. As we can see, this very well matches our first input element A. So this is how secure encryption and decryption happens. As we can see, this is obtained through this formula, which says that our encrypted message when XORed with the key gives us our original message.
So this is how encryption and decryption happens in Turing machine. Thank you.